which word would accurately complete the statement. A runner coming in first place has a blank rate than a runner coming in last place, and that should be B, faster. The reason we bring that up is because we're going to begin talking about kinetics today, specifically rates of reaction. And the rate, the speed that something is happening, deals with what we were just looking at our starter question with. And we've got a nice little guy here that blew himself up because he was thinking, I don't have enough time for this lab. How can I speed it up? Well, he didn't do it very safely, so we want to avoid doing that. So the rate of a chemical reaction, in science speak, says that the speed at which a product is formed is measured as a change in the concentration divided by the change in time. In normal speak, what are we really talking about here? Well, it is how quickly a reaction occurs. It's not talking about how far the reaction goes, so whether we create all of the product or not, we're just talking at, in a given time, how fast are the reactants changing into the products. And I want to remind us all here what concentration is represented by. And we took a look at this. Both A and B are the same answer, so they both work for us here. Other things that represent concentration are moles to the liter -1. We've got moles over decimeters cubed. We also sometimes, not as a unit, but write down when we're dealing with concentration as a lowercase c or a capital M for molarity. That's another word for concentration. And sometimes we just take whatever we're looking at and put it in brackets, and those brackets are telling us that we are determining the concentration of whatever that item is. So looking at these, we've got a car resting, fireworks, and frying an egg, and the fastest initial rate of reaction is definitely going to be the fireworks. We have a very quick reaction happening in a very short span of time. So if we take a look here, we've got some red reactant going into a beaker, some green reactant going into a beaker to form some blue product. So we're looking at what the concentration of the reactants would do over time. Well, over time, they're going to decrease in concentration because the reactants start forming the products. If there's less of the reactants there, then the concentration is lower. The concentration of the product then over time is going to increase. So concentration of the products increase over time because the reactants are turning into those products. So if we want to do a graph of this, we know that initially things are going to be happening quickly, and over time there's going to be less of the reactants, so they're not going to be reacting as quickly, so it's lower slope. And the products, there's going to be less things forming them, so there's going to be a smaller slope there as well. So we can look at this graph. This is just an example of it. The line going down, the concentration is decreasing with time. Those are my reactants. So that would be my red and green from the last slide. So over time, those are decreasing. They don't go down to 0 here, but we see that they start leveling off. The products are the opposite. They are quickly forming at the beginning, and we get a slower and slower rate with time as less of the reactants are able to form those products. So how is it calculated? First of all, we need to know what some different letters represent. So if we have a general reaction where we have some reactants forming some products, the little r stands for the mole ratio of the reactant. Now most of the time we're dealing with more than one reactant, but here we're just simplifying it. We're saying I have one reactant, I'm forming one product. The molar ratio is that lowercase value there. The uppercase letter is whatever my reactant is. Maybe it's sodium chloride, maybe it's chlorine, maybe it's molybdenum. Whatever that reactant is just what we would write that symbol for there. It's forming the molar ratio, that should say ratio, not ration, of the product, the molar coefficient, and the product, whatever that product is. So here's our big equation to memorize. How is this going to be calculated? First of all, we take 1 over the coefficient of whatever my product was and multiply that by the change in the concentration of whatever my product is divided by the change in time. That is equal to negative value of 1 over the our coefficient, the reactant coefficient, times there should be bars around here, the change in the concentration of whatever my reactant is divided by the change in time. Notice here that the reactant is negative. That is because the reactants are going away. So we have a negative slope while the products are being formed. We're generally dealing with rate as being a positive number in general because we've got some change over time. That negative is kind of like the exothermic, endothermic we were dealing with before. It's just telling us what's happening. Here, they're going away, they're being consumed, so it's negative, as opposed to positive because we are forming them. There's going to be more of them over time. So here's a little example for us. We have nitrogen and hydrogen gases reacting to form ammonia. Well, first thing, we don't know what our molar coefficients are until we have a balanced equation. So I ask myself, nitrogen's all on its own. Is it a diatomic molecule? Sure enough, it is one of our diatomic molecules. So I have an N2 reacting with hydrogen gas. Well, hydrogen's all on its own there too, so I have to ask myself, is it diatomic? Yeah, it is a diatomic one, so H2, and it forms ammonia, NH3. To get this to balance, I see that my nitrogens are not the right number. I have 2 on my reactant side, just 1 on my product side, so I'm going to start by putting 2 as a molar coefficient in front of the ammonia. And I see that my nitrogens are good now, but my hydrogens are not. I have 2 hydrogens on my reactant side, 6, 2 times 3, 6 on my product side, so I'm going to put 3 as a coefficient in front of my H2. Now that I have that, I can start figuring out what I'm given and what I want. And I'm given 2 pieces of information. I am given that the concentration of NH3, one of my products, is equal to 0.075 moles over liters, or moles over decimeters cubed. Again, that's one of those things we have a lot of ways to represent it. We are also given the delta T, which is 1 minute, which we're going to do as 60 seconds. We want to deal with seconds as opposed to minutes. So I need to look at the equation that I had before, which is, and I'm just looking at one part of it, I know that my rate is equal to the positive 1 over the product times the delta concentration of product over delta time. So I have a coefficient here, that's my number of moles, 1 over 2 times my NH3, which is 0.075 moles over liters, divided by 60 seconds. So when I calculate that out, I get 0.00063 with the correct number of sig figs moles over liter seconds. So that is my initial reaction rate, how quickly I am forming NH3 in the first 60 seconds. Well, then it asks, what is the rate of the nitrogen at which nitrogen is consumed? So I have this half of my reaction already, or my equation already figured out. The other part of that equation was the negative 1 over the coefficient of the reactant times the change in the concentration of the reactant divided by the change in time. I'm looking for this part right here. And that part right there is equal to what I figured out for my initial rate of reaction for my product to start with. So I can fill this out. I've got a negative 1 over, well, nitrogen just has 1 as its coefficient. Its molar coefficient is 1, so negative 1 over 1 times my rate, the delta chain concentration of R over delta T, is going to be equal to 0.00063. I want to get the rate here on its own, so I'm going to multiply both sides by a negative 1. So it cancels it out on this side, and it just makes this side negative. So my rate that nitrogen is consumed is just the opposite of what I calculated for my NH3 being produced. Hydrogen, we're going to attack this problem the same way. I'm going to have, though, this time a negative 1 over 3, because 3 is my coefficient for H2, times my rate that I'm looking for, my delta concentration of the reactant over delta T, and that is equal to my value that I determined for my product, 0.00063. And I forgot my units here, moles over liter seconds. Moles over liter seconds. So to get rid of this, I'm going to multiply both sides by a negative 3. Cancels it out on this side. Multiply by a negative 3. And I get a final value equal to negative 0.0019 moles over liter seconds. Okay, the next one, we talked about these before, the different things that affect the rate of a reaction. We had that we could add a catalyst, temperature changes, concentration changes, surface area changes. If we're dealing specifically with a solid, not when we're dealing with liquids, but with a solid, we can change the surface area. Pressure, stirring something or not are all ways that we can affect the rate of a reaction. These two videos are good ones. If you have a time to check those out, please do so. This one deals with the reaction rate and concentration, and the big key idea to get from that video is that it's an increase in concentration that increases rate as opposed to increasing volume. Increasing volume is not going to do anything if the concentrations are the same. That's because as you increase the concentration, there's more particles. If there's more particles within the solution, they're more likely to hit, which means they're more likely to hit in the correct orientation with enough energy for a reaction to occur. So I'm increasing my chances of a reaction if I have a more concentrated solution. The second video is dealing with reaction rate and surface area of a solid. Again, we're dealing with solids specifically when we're dealing with surface area changes. If I increase my surface area, that is going to increase the rate of a reaction.